All right, hello ladies and gentlemen. We are about ready now to get started with our next speaker on the Design on Cloud Pavilion, which has been sponsored by Google Cloud and Microsoft. Thank you very much again, guys. I'm pleased to announce that our next panel session is going to be kicked off by John Ellis, who is the CEO of the Silicon Integration Initiative. So let's please give them a warm welcome.
Thank you, Jarek. So thanks for attending today, and thank you to Google and Microsoft for sponsoring the pavilion here. Today, we're going to talk about OpenAccess. So if you're not familiar with OpenAccess, where have you been? OpenAccess has been around for a number of years, and it is really the driving database behind mixed signal analog designs. Without getting into too much, what I wanted to talk about first to kick things off is OpenAccess relevant? Has it improved the interoperability of design flows? So this is a survey we just recently did. In fact, we'll be discussing tonight at our membership meeting. And when we asked designers, has OpenAccess improved interoperability? And predominantly, even with just a little, moderate, a lot, a great deal, the vast majority said yes, it's helping interoperability. But are there still interoperability roadblocks that exist in the design flow? And the answer was also yes. Now these percentages add up to more than 100% because they could answer more than one of these, yes. But the top answer was vendor does not use OpenAccess. So we still have some work to do. And also in our survey, it shows that there's quite a bit of time spent in doing data translations between tools. And this certainly would help things out if all vendors would get on board with OpenAccess. So, upgrading OpenAccess. We're going to talk about that today. There's some big upgrades coming. I'm not going to steal any of Michaela's limelight on that because she's been hard at work getting this work done. But just to remind you, this database is used for production. And all the leading edge chips that are analog mixed signals and some others, digital, they depend on a reliable open access database, so you just can't go in and make changes as rapidly as many people would like us to do. It's akin to working on a live body without killing it. And so it's important to take our time, do it right. But the good news is significant change is coming, and that's what we're going to talk about today. So our panelists, we have three very prestigious panelists. If we're going to assemble anybody to talk about open access, how it works, the nuts and bolts, how it's used, and even some of the latest changes. These are the three. Michaela has been with Cadence. She came to Cadence in 2003 just to work on open access. And even though it shows that she's product engineering director, she just got a massive promotion. Okay, it's a pretty good promotion though, still. She'll take it, and I don't even remember exactly what it is. You could remind me when you get up here. But her background, she started in EDA in 1983, worked for HP, worked for Agilent, all in databases. She had 20 years of experience even before coming to Cadence to work on open access. She received her bachelor's in EECS from Princeton, her master's in computer science from Stanford, so she knows what she's doing. We feel blessed that she's here today because in the past year she's been backpacking, mountain biking, canoeing during the DAC season. So an opening came up. Glad you're here. Next is Dr. Leon Stock. And I think most people know who Dr. Leon Stock is. He's been active. He was chair of Si2. He was chair of DAC a few years ago. He's an IEEE fellow. On top of that, he's vice president of EDA at IBM. He's had many positions there over the past 30 years. And Leon uniquely has a vision to take the CAD industry up to the platform level. And he's going to address that today in talking about machine learning and what can be possible at this platform cloud level. So on the board, he's been a visionary. Some of the work that we've done this past year that Jake's going to talk about in looking at next generation databases was driven by Leon's suggestion in a board meeting. So we really appreciate his guidance. So Jake has been at Si2 probably about 10 years, but before that he's had 30 or so years of experience. What's unique about Jake, he not only has EDA software design experience, but he also has years at National Instruments, National Semiconductor, and Toshiba doing chip design. And in fact, it's fun to hear some of his stories about working on the Apollo program. He has a great interest in astronomy, but he actually worked on the Apollo program. So he's had lots of experience. So when it comes to some really tough projects, and this past year, particularly in system power modeling, Jake has been our go-to guy that literally can do it all. Not only in engineering, chip design, programming, but he also has an MBA as well, top honors from Duke. So this really is an esteemed panel, and I think you're going to look forward to what they have to say today. So, Michaela?
Thanks very much, John. So I'm going to talk a little bit about OpenAccess, a little bit of its history, and the current challenges facing it, and how we're intending to meet those challenges in our next big upcoming release, 2260. So for those of you who aren't familiar with OpenAccess, it is an Si2 standard API used to represent IC designs everywhere from logical netlist all the way through tape-out. It's unique, though, in that it's not just a standard on paper, but a reference implementation is available to Si2 members and OAC members, both the documentation and the source code. The database isn't just for interchanging information, it actually provides a good basis for the applications in memory data model. It's high performance, we work to minimize memory usage and are continuing to work on that, as I'll be talking about later. It provides an efficient object-oriented API, and it is highly extensible. And as John said, it's been qualified in a number of high-end commercial EDA tools that run right on the data model and depend on it greatly. I think, though, the thing that's been important about OpenAccess is that it has what I call good bones. It's really been built to evolve in a stable way. And that's, to me, it's based on two different things. First of all, we hold the API to be drop-in compatible within a given stream. And even between streams, it's rather unusual for us to break API compatibility, meaning that your application can continue to work with new versions of the OpenAccess shared libraries. The second piece is something we call feature-based compatibility, or FBC. We introduced that really early on to allow applications to gracefully tell whether or not a given database might have a new data feature that has come along since they were last compiled, and hence perhaps that application can't work with that particular database. So these two pieces of capability have allowed OA and the applications based on them to evolve over time and to keep customer flows reasonably stable. And so in the last 14 years, we've had somewhere on the order of 100 releases of OA, including 5 new data models with new features, new functionality, performance improvements, and about 1 million bug fixes. So here's a brief listing of the different kinds of releases we've done over the years, kind of by year. Everything from new features such as ability to group shapes or to integrate incremental technology databases. Lots of changes having to do with advanced node, new constraints, a lot of capacity improvements. All the way back in 2005, we had to bump up the number of shapes you could represent. More recently, we had to bump up the amount of data used to represent strings. We've also allowed you to store a compressed version of the database on disk, which saves you disk space and time, particularly for those of you with slower networks. So then what's next? Chip data is getting bigger, and everybody puts up this slide, right? But the question is, what can we do about that? It turns out that the cloud is providing much more capability at designers' fingertips. It's a lot easier for a designer to have access to lots of processors or servers with many internal processors, so that they really have a whole lot more power at their disposal than they have had traditionally. So how do we take advantage of that? How do we enhance open access so that it can better serve applications running in parallel? Well, one really important thing is to be able to have finer granularity in the amount of data that you pull into any one of these processes running in parallel. So we came up with something called OA partitions. Now, OA partitions allow finer granularity in terms of pulling data out of the database, but OpenAccess has already taken some steps down this road. Today, if you have an application that just cares about shapes and vias, you can read in just shapes and vias. You don't have to read in nets. The problem is, once you read in one shape, you've read them all in, and that can be a ridiculous amount of data. So the question was, what can we do about that? Now, partitions are a new data object that allow applications to customize and organize the data on disk so they can pull in just what they need. Specifically, it allows you to take the data of a given type and partition it into separate pieces, separate partitions, and then later you can load those individual partitions in order to improve your performance and capacity. Partitions are new database objects, and hence it's a new, we're going to have a new data model, DM6, if you have partitions in your database. Bear in mind, if you're going to adopt 2260, just saving an existing database with 2260 doesn't mean it's going to be DM6. You actually have to create a partition object for it to be tagged as DM6. That's the feature-based compatibility working for you there. So let's give an example. How would you use this? Say you have a distributed application that today's got, or typically it might have 16 processors to analyze layout. You can run these 16 processes in parallel, so you really want to divide up all of your geometrical data into 16 pieces and allow each application to read in just one tile. So the application would choose their partitioning strategy, and in this case, you could write a really simple-minded algorithm that would look at the bounding box of the design and assign a shape to a partition based on maybe its lower left coordinate. Probably would think harder about that and maybe write it a little bit differently, but that's a very simple example. So then when you turn around and want to use this database, you start up your 16 processes, launch them, and assign each process to read the data from one tile. Analyze the shapes, report back to the master process, and finish. So the message about OA partitions is it enables applications to partition their data, to control how much data a given process has to load, allowing each individual process to use less memory, read in less from disk, and hence run faster. While we were working on this, we also started seeing reports that some people were running out of room for a few other different types of data. We had a 4 gig limit on the data used to represent points and polygons and other objects, so we bumped that limit up. Same thing for some user-defined data called app props, so we bumped that limit up as well. These are totally internal changes. No application code change is needed. Again, only data that actually has more than 4 gig of point, array, or app prop data is going to be marked as DM6. So Cadence is going to contribute OA 2260 to Si2 later this summer, and then it'll then be available to the Si2 coalition members. And I think OA 2260 is really continuing the time-honored tradition of providing a stable platform for IC design applications while evolving to meet the new challenges that were faced in chip design. Thank you very much.
Okay, thank you very much. This is actually a perfect introduction to kind of the next piece. We are a very long time open access user and have deployed it through many of our tools and taped out probably the largest number of chips of anybody out of a full OA database for many of our large systems, including basically the if you go in the back here, you see the IBM booth, yeah, where the AC922 is on display, which was declared the #1 in the top 500 supercomputers as of this morning. So you see just one little drawer right there that you can look at when you walk out here. Okay, so how does this fit with OA? So a very simple message that you need to take away. Yeah, it is time to own your data. Yeah, this came from freeyourdata.org. Yeah, I think this is as much true as it is for your Facebook data as it is for your IC and chip design data. Yeah. Why? Because if you want to apply real analytics, if you want to apply real machine learning, you better have access to that data. You better have access to enough of that data in all its gory detail that you need. So why? I mean, I think if you walked around this conference, it's machine learning, it's analytics, it's everywhere. Right? If you have missed that, then I think I don't know where you have been. Yeah? So why is that? Yeah? It's simple that basically our capability of our tools and the compute capability in cloud have basically surpassed our human ability to deal with this huge flood of data. Right? Basically, the amount of design data that we can generate now is like outrageous. Yeah, because the tools have become faster, we run on huge clouds. So the only way to dig into this is basically good analytics, good visualization, good machine learning to make sense out of this stuff. Unfortunately, to do that, you really need to get into the core piece of your data. Yeah, we have all these tools built on our databases, and we get reasonably good enablement from the vendors kind of to build our own flows. Right? There are a lot of scripts available kind of that allow you to put your own good data flow together. Unfortunately, very few give actually deep data access down to the data that you need to get to do meaningful analytics and meaningful design learning. Like, it's very tough basically to go through the layers that you see here and go through the flow layer to pull out the enormous amount of data that we need to basically feed a good machine learning engine. The good part is, if you use OpenAccess underlying your tools, you actually have the ability to basically just reach down into every piece of data. So as Michaela showed, the API has been nice and stable and constant. And the other great thing is you can get access to every piece of data that is relevant to your chip design. And I'm also very excited about your partition load capability, correct? Because it means you can get access to all of it, but also to only part of it when you want to get to it really fast and do really interesting machine learning and interesting capabilities, analytics on this. So for example, what have we done in IBM? So one of the key pieces, we have taken OpenAccess, which basically has all the physical netlist data. Unfortunately, it doesn't have timing data in there. So we married this up with Neo4j, which is a very fast timing database to basically record all our physical data, but also record all our timing data. I won't say too much about Neo because I think Jack will give us a lot more detail how he's using this for power type of data. But the great thing is, this allows us to store the entire hierarchy of a full chip, from the very top down to the goriest detail at the leaf of your design. It allows us to take many snapshots over time, correct? Remember when you go on Google, and you want to know the critical path, how long is it going to take you from here to San Francisco Airport? The great thing is you can ask about it now, but you can also ask about it at 6 p.m. tonight, correct? Where it looks at historical data and kind of shows you the critical path, how it evolves. Extremely useful data for our chip designers who really want to kind of know, okay, what was my timing yesterday? What is it today? What changed? What happened to my data? We can actually slide through it and show you how critical timing paths actually map out over time. And we can do this incredibly fast by having our cloud generate huge amount of data, cache it up, and basically use the graph NOA to pull all of that data out and access this. So one quick example is basically going through timing. Okay, if you only can go through the layers, the flow layer, you have to write out huge endpoint reports, compress them, uncompress them, parse them, hope that you eventually find the right path in your chip in this pile of data. If not, you have to rerun. If yet, you can actually get it out. This can be a multi-hour type of job. If you basically have saved your entire timing graph in a graph database, So first you have each and every path. Yeah, you have each and every path. You didn't miss anything. Yeah, a graph database is phenomenal data structure that really does this. In addition, you can query this with one very powerful line in a second. Yeah, and you get instant data no matter where it resides in your chip. So matching this up basically with the physical availability and the physical viewer on top of OA that you see, for example, on the left side here. Yeah, we built basically a web-based interface with on the right side our timing visualizer, which basically runs on top of the timing graph. The left side, our physical design system, which runs on top of OA. And basically it's linked in the background together, and you can do this full chip, real time, all the time. Yeah? Pretty drastic paradigm shift from basically running tools, waiting for data, running scripts, writing a couple of million or a couple of thousand lines of Perls to dig through billions of lines of data to actually find what you're looking for. Yes, what we are really bringing to our designers is a very different experience when they run on the cloud versus running individual tools. Yeah. OA is a key piece of this. Certainly, I mean, OA is very effective in getting us to all the detail of the data. It was a little bit less effective to serve up data really fast, but I think these partitions are going to help. Yeah. So we built another structure on top of it that we call DD, which is kind of a caching structure to make sure that we can get to the physical data as fast as we can get to the timing data. But overall, this has been a very interesting kind of productivity improvement and allow us to really start to take full advantage of cloud scale technology in the EDA design flows. So I only talked very shortly about kind of the data aspect of this here. If you want to know more how are we actually using this and put a whole tool architecture together, Kareem and myself will be talking this afternoon at the same podium here at 2:30. If you want to know how we apply some of this in our functional verification flow, on Wednesday at 2 p.m. in somewhere upstairs, yeah, we'll have another talk talking a little bit more about our verification flows. So in summary, all I want you to remember, that open access means open access to all your data. If you believe that machine learning analytics is the future, you should not only own your data, you have to have full access to your data, because owning it, yeah, with only being able to get there through some tool interface that gives you only half the data or very few data at low bandwidth, doesn't do you any good if you want to build some substantial machine learning capability on top of this. So that's what we use OA for. I think OA is getting there. It is almost good enough. As I said, it gives us all the data, and we are really looking forward to speeding it up and really getting all the data out as fast as we need it, kind of to feed all the analytics and machine learning. With that, I'll hand it over to Jack, who'll talk about another real interesting application.
Thank you, Leon. So, launching open access data into the cloud. So we're going to take a big open access database, slice and dice it up using OA partitions, put those partitions inside of little data containers and launch them into the cloud. So why are we doing it this way? Well, first of all, this big thing on the left here is too big to go into the cloud. And I'll explain that next. So here's the good old days. We had single-threaded computers, but we had exploding data complexity. We had increasing integration. As you can see along here, as you did stuff, it gets harder and harder, more and more steps, more and more timing, more and more checks. So we had more integration. And at 22 nanometers, we had 20 terabytes of information. So this is around 2012. Where Miguel mentioned that we had a scratch data space, so that's that scratch is at the very top, and you see 20 megabytes of data. Now, take a look at this. This design data is so big, right? It takes 2 horses to pull it. Now, why is that? Well, remember, I started 40 years ago with Calma, where we had 10-inch tapes, 9-track tapes. They hold a gigabyte. We have 20 terabytes. Okay, that's 2 million tapes. Right? It's much bigger than that wagon. 2 horsepower, what is that? Well, horsepower is 756 watts. So it's 1.5 kilowatts to move that wagon. Move it at 1 hour, right? That's 1.5 kilowatt hours. My Tesla takes 400 watts to go a mile, for an hour, right? So big data, we got to get smaller. As Michaela said, finer grain on your data, more modular data, data that looks more the same, data that can be used many different places at many different times. So here's an example. We're getting lighter, more modular. We're not in the cloud yet, but we're in the trees at least, right? We have the data, now more modularized. It's going to be squared up, made, and so once it's modularized, you can package this up and ship it anywhere. You know, we live in a place where it has to be there overnight guaranteed. The furthest that horse-drawn carriage goes is 10 miles in a day. How are you going to get that to China? How are you going to get that to Taiwan or to Japan? You're not going to get that data over there. But now we have 64 cores, actually 32 cores, 64 threads coming out in Q3. That's the Ryzen from AMD. Intel has a Xeon processor, 28 cores in it. So lots of cores, lots of threads becoming available. Well, listen, when you have 64 threads available, you better figure out how to use them, right? And that's what this does. So more cores, more threads, more memory bandwidth, and more modular data that can be used either locally on this laptop, or if there's a server farm next door, right down the street, right down the next booth over, server farm, you could have thousands of threads, thousands of cores. And we are using analytics and data visualization. So here's an example of an 8-core die, each one of these is a core, stacked on top of some DRAM, and we're looking at the thermal analysis where these hot cores are making that DRAM hotter but right below them, and so we have to refresh that DRAM more often. So this is what our data container looks like. The first thing you'll see is a time slice on top. That's because we have 1,000 time slices. You send them off to 1,000 computers, they may come back in a different order. So after they come back, we reorder them in the right slice order. We also have different modes in this. This is a power demo we're giving at the Si2 booth Tuesday and Wednesday. We have these instance conditions, which are different voltage and temperatures per instance. So if you have 1,000 instances, you can have 1,000 different voltage and temperatures, and safe activity. And safe is a switching activity file. We have simulation of the switching activity. We have the voltage and temperature. We figure it all out. And down here, you see we have a model that uses data analytics to calculate the power. And we calculate both the dynamic power and the static power across voltage, temperature, and frequency per instance for thousands of instances. And it's really good for computerization, analysis, and visualization. And it can either be done locally on your laptop or remotely on a server. It doesn't really care. Even on a laptop, it uses a loopback to make it look like it's a server. The other thing we get out of it is that we have these nice graphs that we can view. This is a graph of Verilog connectivity inside of OpenAccess. So we basically ran Verilog to OA, then ran OA to Neo4j, and build a graph of the instance connectivity. And as you can see, we can do millions of instances in a minute. This is, connectivity, looking at layout is pretty simple. Looking at connectivity isn't that simple. So having the ability to visualize concepts like connectivity is really important. Also, we have built-in multi-threading. So the minute you go to Neo4j, you automatically have built-in multi-threading, data encryption, and database reliability. And one line of code with Neo4j can either create a netlist with all the capacitances, it can create the static and power at any voltage or temperature, it can create the dynamic power at any voltage, temperature, and frequency, and Verilog simulate activity. So we take 2260, we have a common SIG framework, which is how we support these 4 scripting languages. So OA supports Perl, Python, Ruby, and Tcl. We have an OA cloud interface that we did for our demo that you can see. And then we have Cypher is the name of the scripting language that runs on top of Neo4j. And we take the data out of OA, goes into power predictions, or in case of Leon, it would be timing analysis, or in case of something like Opal, it would be pattern analysis. So we're taking these slices of data out of OA into the cloud. So in summary, 2260 has selective access to OA data. so you can transfer small data containers into the cloud for parallel execution of multi-cores and threads. As chips become more complex, you need more data analytics to observe the profiles of voltage, temperature, and frequency set points and time slices and things like that. The core wars have just begun. Next year or two, you're going to see bigger and better and faster chips and bigger and better, faster server farms. You better figure out how to use them in your EDA application. OpenAccess is the industry standard for building SoC devices. Whenever you see mixed signal, analog, and digital on a device, it's probably, most likely, on OpenAccess. And we predict that OpenAccess will continue to excel as a large repository database that remains on the ground, but launching smaller data containers into the cloud for parallel processing. That's it.
Thank you, Jake. So now we have some time for some questions. And I'm going to kick things off with a couple questions here to get things going. And then I think we have another microphone we can use to pass around. Great. Okay. Marshall, if you could get that. This is Marshall Tyner. He's our director overseeing OpenAccess. And actually, I'm going to give a plug for OpenAccess and the coalition. A lot of the things you saw up here today are a result of the community that is OpenAccess. It's not just a means to get to the code and get to the downloads, which is really important, but it's a means to ask questions, to get questions answered from Marshall, from the community members, from Jake and others. And so some of this is a result of the things you learned by joining the OpenAccess community. So my first question is for Michaela. Just to make things clear on OA 2260, is it drop-in compatible with applications that are compiled with 2250?
The API hasn't changed in that there's just new APIs added. However, there is going to be a change in the supported platforms, and particularly the GCC compiler. We're moving to GCC 6.8. So if you, for example, have plugins that you're accustomed to using and they were compiled on GCC 4.8, I think it was, and you want to use them with newly compiled OA 2260 shared libraries, you'll probably have to recompile your plugins.
Okay. Okay. Next question is for Leon, and hope this makes sense. I was looking at our survey data last night, and I saw that over 80% of chip makers, they still develop their own design tools internally. That's interesting, and most do so. Survey says first to get a competitive edge, and they feel their own problems are unique. They can't, I guess, collaborate well, or they need to just do it on their own, and they need better performance. So do you see machine learning being an area where general solutions built on top of OA can be provided? Are chip makers going to have to roll their own, or is it going to be a blend? Where do you see that going?
Actually, interesting, you're 80%. I think that might be a little bit dependent on kind of who you serve. You serve OA users, I guess, and these people, I think, are by definition interested to actually build something on top of it. So, but I think it's healthy to see. I think what we are seeing really come back together is the differentiation in your design that needs to come from the knowledge that's embedded in your data and into your tools. So I mean, I am still very fortunate in IBM that we have been able to have a good mix of tools that we own, tools that we procure from various vendors, and a database like OA that allows us to glue the stuff together.
Yeah.
Which means that we still have the ability to build a lot of, I would say, interesting differentiation on top of this. I think with the advent of machine learning, I think we had a machine learning workshop yesterday upstairs, and I think the biggest question that was asked every time again, who owns the data? Is it going to be the EDA vendor, and is he going to be able to take your data or your trained model and then apply that to your competitor? Or do you as the user of the tools own that set of data? I think that's going to be a very, very interesting question, right? Because I think we all have a pretty good feeling that a lot of the knowledge is going to be encapsulated in the models, which are going to be based on the data. Who owns the models? Who shops them around? I think the good thing is I don't have to answer that question immediately for IBM, because I think we have enough control over all the components. And I believe more people are going to feel that pressure and starting to kind of position themselves in the spot that they want to be in this emerging, very data-centric, model-centric kind of evolution, of next evolution of EDA.
Wow. I can see where that could be an issue. Back at Semitech, we had a similar issue with remote access to tools, remote diagnostics, and who owned the data, for what purposes, and under what conditions. We had to get all that sorted out to break things loose. So, well, Jake, I have a question for you, because you've had so much experience this year with using Neo4j and seeing where things are going with 2260. You may have pretty much answered it on the last slide, but I want to get confirmation. We've heard some folks say that, at least they've asked Marshall this, or told Marshall, they see OA, it's kind of reaching a dead end. But with your experience this year and your knowledge of what's coming, what's your feeling on OA's continuing relevance?
Well, OpenAccess will always be the database, the industry standard for SoC devices. So look around, there's one right there, SoC. Whenever you see that word SoC, right, means save our chips. That's about a IC design that's going to have analog, that's going to have mixed signal, that's going to have digital, that's going to have big blocks, it's going to have little blocks. Now, some people use more than one database. I think Leon has more than one database. But for SoC, I think the database, vast majority of the respondents, right, for SoC, the database to use is OpenAccess. Now, when you have all that data, it's going to be 20 terabytes. So it's not easy to put 20 terabytes into the cloud, but it is easy to slice and dice that data, put it into modular containers, and put those containers into the cloud, and have them process in parallel, and then bring it back into OpenAccess at the end. So yes, OpenAccess is alive, well, and going to be growing, getting taller and bigger, and going into the cloud.
Good answer. Is there a question from the audience?
Yeah, I've got a question about the OA partition capability. I can see how that could really be useful for the high thread count, high core count applications. And wondering about the OA reads, and are there modifications that will have to be made to the code in order to get through standard OA reads with existing code?
So it kind of depends on the application. If you wrote a partition savvy application that you want to make sure is just pulling the data that you need, then you have to have kind of a pre-processing step where you divide the data up into those appropriate partitions, and then your application has to be able to assign them to your different processes that are running. Now, if you are not an OpenAccess or an OA partition savvy application, you might still get some benefit because we will load by partition implicitly. So just like we load today by data object type implicitly, like you're not writing any special code to say, I just want shapes. When you ask for the first shape, you get it, the whole table in, but since you haven't asked for nets, you haven't read in nets. With partitions, if you ask for shape 297 and it's in partition 46, you'll get partition 46 in. If you then jump to shape 29 and it's in partition 308, you'll get partition 308. So if you have a relatively well-organized partitioning strategy that happens to work well with that application, you'll get a lot of benefit out of it. But you'll get the most benefit if you know which ones you want and you go get them.
Any other questions from the audience?
You mentioned that you might have to recompile code for 2260, but do you actually have to change any of the source code?
If you don't want to use partitions, then you don't have to change any source code, just recompile and go. Oh, one more thing. If you want to be able to read, a database with partitions, you have to make sure that in your OA design init that you're kind of inheriting the most recent DM revision number, as opposed to having explicitly written in DM4, DM5, DM6. So you have to rely on the definition of the most recent DM version that's in the header file. If you're doing that, you don't even have to change any code.
It's got to be 2260. It's got to be 2260 DM6, and so you got to make sure of that.
Okay, any other questions?
Kind of a personal questions to the panel. When it comes to data, okay,
Yeah.
I don't want to be too loud.
Too loud's good.
Okay.
It's hard to hear.
You mentioned data is the important point. How about owning the data and making sure that no one gets to your data, and you can be certain that no one's going to hack it? Personal question.
All right, so let me answer how we did it in our demo. The way we do it with Neo4j is that we have a channel between OpenAccess and a server. That channel can either be encrypted or not, right? It's up to you. We don't encrypt it because, well, maybe we're at DAC, maybe we should be encrypting it. But, you know, we think that encryption is a big part of it. Also modularity. You can take a look at that data that I just showed you. Unless you know what you're looking at, it doesn't make a lot of sense to you because that's just one slice in time. It's like one snapshot, and you don't get a full picture just looking at a snapshot. So yeah, if you stole 2 or 3 data containers and decrypted them, you still wouldn't know what was going on.
Got it. Thank you.
Any other questions? Well, if not, I'm going to make a plug for our members meeting this afternoon at 4 o'clock over at the Marriott. You have to be an Si2 member, but we're going to have a panel discussion on that same survey I've mentioned a few key data points from, and that's going to be interesting. We had about 120 participants from the industry that answered 59 or so questions, and we got some interesting results. So I'd like to thank our panelists.